Today's topic is design of tension members. Let's first discuss few applications. The tie member or the bottom chord member in roof truss is a tension member. In case of top chord members of the trusses, the sag tie or sag rod are tension members. In case of braced frames, the bracings are the tension members, and same as suspenders in suspended buildings. These sections are used as tension members. Single angle, double angle members, channel members, I section, rod and cables are rolled steel members, and the section data are available in Indian Standard Code, which is SP 61 1984. The built up sections are developed here using the rolled steel sections. The double angle sections should be connected to each other using bolted connection or welded connection. Rivets can also be used. Let's first discuss the tensile behavior of steel members. The tensile characteristic of steel is represented here using a graph at which the tensile force is represented in the ordinate and the tensile deformation delta is represented as an abscissa. This is the force deflection curve of a mild steel bar. At point A, the curve begins, and at point B, the yielding of the material begins. At point C, the yielding finishes, and at point D, the ultimate strength of the mild steel bar is achieved. At point E, the material breaks. The curve from B to C represents the yield behavior of the material, and the yield deformation of mild steel is almost 10 times of the deformation at which the yielding begins. This is the force deflection behavior of a high strength steel bar, and this is the ultimate strength of the high strength steel bar. As we can see that in case of high strength steel bars, no definite yield point is available, so we have to use the proof stress concept. Now to achieve, or in order to have the proof stress, we should have to consider the tensile stress or tensile deformation at 0.2%, and we have to draw a straight line which should be parallel to the initial curvature of the force deflection curve. Now the line will cut the force deflection curve at this point, and the corresponding stress is termed as the yield strength in case of high strength steel bars. This is the reserve strength in case of mild steel bars, and this is the reserve strength in case of high strength steel bars. As we can see that the reserve strength of the mild steel bar is more than the same for the high strength steel bars. Now let's discuss simple plate subjected to tensile forces. The possible modes of failure are gross section yielding, net section rupture, and block shear failure. First, we discuss about cross section failure of a plate shown here in yellow color and subjected to tensile forces. The tensile forces are represented here using pink color, and the bar or the plate is a mild steel plate, so that's why the stress strain curve is represented like this. The area under the stress strain curve is the toughness of the mild steel plate. This is the cross section of the plate. Now as the tensile force increases, the stress in the plate reaches up to the ultimate stress. This is the ultimate stress shown in the plate. This could be the possible limit state of failure for the plate, but at the point of ultimate stress, the overall deflection of this plate subjected to tension will be higher than the limit state of serviceability. So we have to limit ourselves up to the yield strength of this plate, and this should be the limit state in case of plate subjected to tensile forces. Now let us consider the previous plate but with a hole in it. Now this is the hole, and we can see in the cross section this is the hole. Now the plate with hole subjected to tensile forces, and at the yield point this should be the stress distribution along the hole. This is in the elastic state, and as the force increases more, the stress will reach in a elastoplastic state, and we can see that the stress around the hole is now constant, and it is at the value of yield strength. Now the stress around the periphery of the plate increases, and it will reach up to the ultimate stress, and when the stress condition of the plate is plastic. Thus the limit state should be rupture of the net area, and this should be the rupture line of the plate, which begins along the periphery of the hole and it will finish at the boundary of the plate. These are the formulae to calculate the tensile strength of a plate. The first one is to calculate the tensile strength of the plate in case of cross section failure, and the second one is to calculate the tensile strength in case of net section rupture. The TDG shows the tensile force carrying capacity in case of cross section failure, and TDN is the tensile force carrying capacity in case of net section rupture. AG represents the cross section of the plate, Fy is the yield strength, and gamma m0 is the partial factor of safety. In case of cross section yielding, the partial factor of safety should be 1.1. The AN represents net area of the plate, Fu is the ultimate stress of the mild steel bar, and gamma m1 is the partial factor of safety in case of net section rupture, and its value should be 1.25. As in case of net section failure, the plate is allowed up to the plastic state. We are using here an additional factor of safety which is 0.9, and its value is constant. Now how to calculate the net area? Let us consider a plate with one hole. This is the cross sectional view, where we can see that the hole is represented by this diameter d. Small t is the thickness of the plate, and small b represents width of the plate. So this is the net area of this plate. Now in case of two holes in the same line, the formula changes, and this should be the net area, which is less than the first case. In this picture we can see the failure of the net section. Now if the plate has two holes but they are in different lines, then we have to consider two cross sectional lines, and we have to calculate the net area along both of these. The minimum should be adopted. This red line represents in the second picture, it shows another mode of failure, and in this case the small p represents the staggered pitch and small g represents the gauge distance, and the net area should be calculated like this. The small p again here is the staggered pitch, and small g is the gauge distance, and we have to calculate a summation of this parameter. All possible failure paths should be investigated, and the minimum net area should be used in design. Now let's discuss about the block shear failure. Block shear failure can be achieved in case of coped beams, angle sections connected through one leg, and in case of welded plates. In the diagram of the welded plates, we can see that these two planes are parallel to the applied force. Hence, these two planes are subjected to shear forces, and this plane is perpendicular to the applied force. Thus, this plane will subject it to tension. Now let us consider two plates connected via bolts. These bolts are marked in the figure using 1, 2, 3 and 4, and this could be the possible failure path. The pink arrows shows the tensile forces here, and the line 1, 2 and 3, 4, these lines are parallel to the tensile forces, and this is why along these lines shear stresses will generate. Now the line 2, 3 is perpendicular to the force applied, and thus along line 2, 3 tensile forces will generate. This is shown in the figure below. Now there we can see a combination of shear force and tensile force is found. Thus, to find out the stress carrying capacity of a plate, we should consider both the shear forces and tensile forces simultaneously. Now, this diagram shows that in these planes, the green arrows show the shear stresses and the pink arrow shows the tensile stresses. Now along these green lines or green arrows, no bolt holes are there. So this is why to calculate the net area in shear for this diagram, we should consider the gross area. Now to find out the net area in case of area subjected to tension, we should consider the net area, because in case of area subjected to tension has bolts. In the second diagram we can see that along these two lines the shear forces are acting, and we have holes along these two lines. So we should consider net area in shear stresses, and along this plane no holes are there. So this is why we should consider gross area in case of tension. These are the formulae to find out the block shear strength of a plate, and the minimum should be adopted in design. Now shear lag parameter will generate in case of members connected through one leg only, like in case of angle sections. Here we can see one angle section is connected to this plate via this bolt, and it is connected through one leg only. Similarly, in case of welded connection also, the angle section is connected to this plate via only one leg. In this case, shear lag will generate, and in Indian Standard Code, the shear lag parameter is represented by this beta. Now, the shear lag will be effective in case of only the outstanding leg, and this is why the shear lag parameter beta is associated with the outstanding leg. Here it is AG0 is the gross area of the unconnected leg or the outstanding leg. This is the formula to calculate the shear lag parameter, and its minimum value in case of mild steel materials is 0.7. These are the upper and lower limits. This is how to calculate the block shear strength of an angle section connected through one leg only. and in case of welded section no net area is found. We have to consider the gross area only. Thank you.